future people, it's the 4th of March, 2024. And we have demos. So let's start with Zach.
Okay, well, speaking of new engine performance, at the end of the week, last week, I did a little bit of experiment to kind of validate what we were talking about with the so-called new engine turbo. And this is going to be one of those demos where I like show stuff in a terminal and talk about it, but always the favorite here. So let's see about that. So what I did was our big theory was that one of the biggest bottlenecks in the performance of the new engine was fetching and deserializing the graphs. The graphs are huge now. You can see here uh, the data fetch for this one was 224 milliseconds, and the graph itself was 15 megabytes. That's this graph here with 118 components on it and some connections. And it has like what, 17,000 nodes, 34,167 edges. So yeah, so what we did was sort of the theory that we go here is if we reduce the size of the graph by making node weights just the hash of their content, and then caching all those node weights in some kind of concurrent hash map where you can look them up really, really rapidly, and then distributing those node weights through some kind of communication layer so that every service has the node weights before they start to do work on the graph, that it will be very fast. And so what I did was just convert the big graph to a small one that is just the hashes of the node weights, and then looked at deserialization performance and things like that. So let's add, I don't know what the biggest component is. The EC2 instance is pretty big. Let's add an EC2 instance uh, to the graph. Ooh, we're doing stuff. It's hard to know which one is the rebase now for the EC2 instance because it hit a blur event when I added it. But here we go. So it'll be like one with about 20 updates because that'll be the dependent values job. Uh, Let me see if I can add one again and get a cleaner log without all those other events from different blurs. Let's add it right there.
This is
Okay.
pretty fast for 120
I mean,
nodes.
it's comforting to see the system relatively purring with that much chaos on the graph.
Well, and this is just
Yeah.
the first pass too. There are so many other performance passes we can do in the future. This is
Yeah,
great.
so there's more optimization to be done. Okay, so this one right here with one update, that's the initial rebase where we add the component to the graph with all of the unset attributes. And so you can see that our big snapshot takes, and this is on a release build, it's actually much slower when you run it in tilt because it's on the debug build, but the release build, you can see that it takes, right, it's like it's 270 milliseconds for each snapshot. So in the rebaser, we have to take two snapshots, for the current one for the change set and the one you just updated, and you're saying merge these two together. So we do fetch the current one 15 megabytes, the new one is 18 megabytes. It takes a long time to do these fetches, and then the deserialization itself is pretty long. Now, when I shrink the graph to 1.74 megabytes, and that's by just iterating over every node and every edge and converting their weights to the hash of their weight, it shrinks it by, what is that? By a tenth. So it's about 1.7 megabytes. Deserialization is 2 milliseconds, very fast. Um, and then updates you can see are quite fast. So for adding a single component, we can do that with the unset thing. I think we'll be able to do that like under 30 milliseconds probably in total. It gets a little slower here. This is the rebase here with the 21. That's the rebase for the dependent values update job that calculates all of the values for the initial component. So that was 28 milliseconds to figure out the updates, 25 milliseconds to perform them. So we can probably get that dependent values update job running in under 70 milliseconds. And this is without we haven't done any optimization to these operations. Like we haven't profiled them. We haven't figured out, if there's work we're not supposed to be doing in there. There probably is. But let's do another fun one, even more fun, is this region has got a bunch of components connected to it. Let's go to, doesn't matter, we're just picking a region. Okay, we're gonna get a huge dependent values update job eventually. And it'll come through in a second here. And
What
don't,
is the eventually part? Do we know what the what's happening between now and the job being picked up?
I'm not totally sure. I mean, I know that we have to do these fetch and deserial operations in Pinga. Yeah, so we have to trace this all the way through. Here it is, and figure out why it took so long for this dependent values update job to arrive. But here it is with 157 updates. Now it's not like great. 286 milliseconds to perform those updates is not ideal, but I do think that we can get right all these values for this is I don't know. There's like 20 things in this region, and they're kind of spread around. Um, we could update that like the value will flow through for all of them. I think we can get that in under a second for sure. If not under 500 milliseconds for that update. But yeah, so I just wanted to validate that this was something that was the right direction to go in, and I think it is. I think that the outcome is that yeah, this is the right way to get things very fast. Certainly much faster than they are now.
Nice. Well, I'm gonna go next. So trying to validate a similar end of the spectrum. So we had talked about sort of how do we want how do we want to store it in memory? So Zach talked about like trying to sort of store a hot cache in memory as part of that work. So if you imagine those graphs, a huge part of that time was streaming them in and out of the database. So it was just, it was 100+ milliseconds probably just to get the data out of Postgres. So so we've been noodling on the idea of, well, what if we kept the objects in memory? And then in sort of doing a little more research, we started playing around with this idea of like a tiered storage design where it goes from like hot in memory to spilled to SSD to then Postgres sort of at the bottom layer. So I didn't bother to try the Postgres layer, but I did do a little bit of this. So this is like a very simple version of tiered storage where it writes to a cache in memory that is evicting based on attention. So if you stop calling for the object, it'll eventually evict over time, and then spills to disk each time. So this is actually not a 1 meg uh, test. It's actually a 10 megabyte object test. So if you look at, the cold cache insert speed, so this would be if you have a write of a 10 meg object, it takes 26 seconds. That includes the time it takes to create the caches themselves. So including the on-disk database format and all that stuff. So it's actually faster than that. Um, the this is inserting 26 10 megabyte objects. So I know it says 1 meg, it's a lie. Um, and the benchmark for that is going to come out in a hot second here. Yeah, it's estimated to take a little time because it runs a lot of samples to sort of prove that it's right. But it comes out in 200-ish milliseconds, which again sort of speaks to the fact that a big piece of this 26 milliseconds is actually creating the on-disk structures. Zoom tax. Come on. You can do it. I should have shrunk it down to 1 meg before I started doing this. There you go. So on average, 600 milliseconds. So we could have written 25 10 megabyte objects. And then this one is checking cold cache inserts. That was for 26. This was hot cache. So this was if I wanted to retrieve a 10 megabyte object from the cache in memory, it takes 260 nanoseconds. And then if it's hot on disk, but cold in memory, it's 893 microseconds to retrieve the 10 megabyte object. So all that's really doing is showing you that if you think about the like lower bound performance of how long does it take to shuttle the data around, right? We can cut all of the sort of network transit time out in the hot path to be quite quick. And since all the objects in the new engine are immutable, a lot of the complexity around those sorts of tiered storage engines starts to drop away because you don't have to worry so much about writes or any of those things. You're just sort of writing new data all the time. So yeah, it looks like we should be able to put something together that's quite fast in terms of storage. So if you imagine putting on top of Zach's existing work that you sort of removed all of the deserialization time because you were just storing it in memory already deserialized, and you got the lookup time down to nanoseconds. That's sort of what's maybe possible. At the at the at the fastest. Okay. Nick.
Think it's actually going to be Victor.
Hey,
Yeah.
Great.
okay. Yeah, me and Nick worked on this together. Mostly Nick, because yeah, production stuff was also going on. But yeah, we did it. And what we did was put secrets back in the system. So this is going to be one of those demos like, hey, look at this. It looks exactly like it does on main. So as you can see, I've created an AWS credential component and an AMI component, just anything that takes an AWS credential, actually. And you can add a secret. So demo 1, no description. I'll just add a bunch of gibberish here because what matters to us is that the qualification for the authentication function.
Yep.
Thank you. Yeah. Will run correctly. So we'll just add a value here. We've been having some reactivity. Like reactivity is not set up 100% still. So sometimes you need to reload when you create stuff or when you set values. And there's this, the qualification here. And as you can see, this happened here. This is a really bad way to show it, but this is what we've got right now. This is like a lang.js log coming from Veritech. And before I set the value, the before array was empty. Wonder if I can zoom in here. Which is how we actually like the before functions, the authentication functions package is just like the lang.js package with the before array with something in it. Right? And after I set the value, you can see that, Jesus. Where is it?
Yeah, but it's
here. So there's a before. Yeah, there's a before item and a before array over here. So it's still failing naturally, but the qualification executed with the before function before it. So yeah, secrets are back in. You can set them and they propagate forward as you expect them to do. Set here. So yeah, one more step towards feature parity with main.
Sweet.
Anything you want to add, Nick?
No, other than this is like the sequel to last week. You know, we added the ability to create secrets and like work with them, and now this is like the full wiring of them. So once we follow up with actions and resources, I think I think as far as like core system capabilities though, we're in really good shape there with the new engine. So yeah. Great progress. Great job, Victor, too. This was also Victor's first week on the new engine and found the bug within the first 4 hours. So, yeah, great work.
Thank you.
All right. Okay, so the feature I'm about to demo, it's not currently working on main because we had to blast away the metadata that it uses in order to improve performance, but hopefully we'll have that metadata back in the system soon.
Might as well put it back now, because who gives a fuck about performance on main anymore? Haha.
Good point. Regardless, I put it back temporarily so I could demo the feature. So we have these wonderful indicators that we've been working on that are really great. But one of the problems we ran into is that while you can change whether something is controlled by a socket or manually, or by a function or manually, by entering data into a field for a prop, for props that are groups like arrays, maps, and objects, there was no way to do that. So we have this cute little dropdown here now. This is an empty security group ID array that is set via a socket. So there is no controls or anything to be able to manipulate it. It's driven by a socket. If I want to change that, I click here and click manually, and it'll take a second, but it'll change, and voila, now I can drive it manually. This feature is working in a bunch of different edge cases that we kept running into. One of those is if I have data that's already being fed in, it will preserve that data. A socket that's currently in use, right, even if it's empty, will preserve. And then also, if you have an object or an mapper array that's inside of another object mapper array that is controlled via a socket or a function, you can't set that one to manual because its parent needs to be set to manual first. So in this example, there is no menu on here. The menu is up here.
Love it.
Yeah.
That's so good.
Well
Data is
done.
preserved, right? You can drive everything manually if you want. And that sort of like ties up and buttons this work on source icons. There are definitely still some minor issues with source icons that we haven't fixed, but they're kind of not worth fixing since we're going to reintegrate the entire system when we switch to the new engine anyway.
Beautiful.
Wendy, that's turned out so nice.
Yeah,
Incredible.
amazing. Really
That
amazing.
actually looks better than we originally talked about. So really nice work there.
Yeah, and that dropdown is prepared so that when we want to start adding the ability to set up sockets or functions via the attributes panel, you could do it via that dropdown as well.
And that's like
Fabulous.
for anybody that's watching. Just
Any last minute walk-ons? Once, twice. Okay, sold. See you later. Thanks, future people.